Alright guys, this is it. The last video for mechanics and the last video for chapter 16. Feels great, even though I'm not done yet. So I just wanted to remind you of something that we looked at last time because I find it pretty useful to sort of lead into what we're going to look at for this lecture, at least part of it, the first part of it. So in the last video, we talked about relative motion analysis, basically the idea if you have, a linkage and you know the speed of one part of the object as it's rotating, then you can find the velocity at another point given knowing the angular velocity and the vector that goes from the first point to the second point. So for instance, we looked at this situation right here where we would talk about the velocity at point B could be related to the velocity that point A has plus the part of it that undergoes some rotation, so the angular velocity crossed with the vector that goes from A to B. So hopefully you kind of are feeling good about that material and you've done some problems by now on that. What we're doing in this chapter, or not this chapter, but this section is we're looking at the situation where what if the velocity at that point A was 0? And so what we're calling this is the instantaneous center of zero velocity. The bicycle wheel, which we had a diagram and we looked at that in the last section, is a good sort of illustration of that instantaneous center of zero velocity. Because when a wheel is turning as the bicycle goes along, traveling from left to right, the point where it reaches the ground isn't really moving relative to the ground. So that's a point of instantaneous center of zero velocity because it has a zero velocity. But because of the fact that the whole bicycle wheel is rotating with some angular velocity, we can express the velocity at different points on the wheel relative to that central point, that zero center point, knowing the distance from the instantaneous center to where we want to know the velocity, and also knowing the rotational rate of the wheel. So that's sort of what we're looking at here. It means that the velocity is much easier to find because it's simply a product of a distance and an angular velocity. Here's another example of a problem where you could use the instantaneous center of zero velocity. A board that's propped up against the wall. 2 points on the board, the point where the board meets the wall is sliding down the wall, and the point where the board meets the floor is sliding outwards away from the wall. And those two velocities are in different directions. But if we remember, in the idea is that if you have some sort of rotation, and then here's your 0 point, and here's your radius vector, your velocity is perpendicular to that radius. And so using that, we know that the radius for each of these velocities has to be perpendicular to them, and if we trace them back, they intersect at a point, and that becomes the instantaneous center of zero velocity. And so we could actually figure out some information about how that board is falling given the fact that we know where that 0 point is. So basically the idea is that if you have an object that's undergoing some sort of planar motion, there's going to be a point on that plane where the velocity is instantaneously 0. It doesn't actually even have to be on the body, but it's somewhere in that plane of motion. And then if we find out where that point is, it's really easy to figure out the velocity of another point because of the fact that the velocity of that point is just going to be equal to well, I should say the magnitude of that is going to be equal to the rotational rate of the object times the velocity, the radius going from B, the point, let's call it B, to from the instantaneous center. So we'll have some better pictures soon. So thank goodness, here's a better picture. So one of the things I already said, but it's true, is that the velocity and the radius vectors are going to be perpendicular to each other, because the idea is that the instantaneous center, in a sense, is like a center of a circle. And so as the body's rotating, it's traveling, that point is going to be tracing out a circle. And so if you remember, if you draw a radius of a circle and then a point on the circle that's moving has a velocity tangent to that, and so those two vectors, the radius and the velocity, end up being perpendicular to each other. And so that helps us sort of trace back to find out where that instantaneous center might be. And then, as I said before, the way that we would write the velocity of A would be equal to the radius that goes to A from the instantaneous center times the angular velocity or angular rotation of our body. And so that's how we can find whatever the quantity is that we want to know, whether it's, sometimes we want to know the velocity, and we're given the radius and omega, and sometimes we have other knowns and we want to find a different unknown. So one of the things to keep in mind is, of course, omega is going to have a sense, and so the orientation of where the instantaneous center will be is going to be determined by the direction of the velocity and also the direction of the angular velocity, so that they have to be consistent. Sometimes, like the picture that I showed you of the board sliding down the wall, means that there's going to be, there might be 2 points that you know their velocities, and then it becomes even easier to locate the point of the instantaneous center of zero velocity, because of the fact that you can draw perpendiculars from the velocity vectors, and then you sort of trace them back, and eventually they're going to intersect, and that location then becomes the instantaneous center. So this picture right here shows that the two intersect at that location. It always makes it a lot easier when we have two velocities to work with, because it makes it so much easier for us to find the instantaneous center. You could also have situations where the direction of the velocities are known, and you could use, and the magnitudes of the velocities, and you can use some, similar triangles in order to figure out where the instantaneous center might be. So, basically, again, what I said previously is, once you've located the instantaneous center, if you know the radius and you know the angular velocity, then the velocity is simply a product of the angular velocity and the radius. And so that's a relationship that becomes really important as we're solving problems and working through more complex situations. Here's one of the example problems. This is actually a problem that you're going to have to do when we meet for class. So here, this is a good this is a good situation where we have two velocities. So like, for instance, here we know the velocity of D looks like this, but at the same time there's a velocity of point B, and so we can trace back from those points to see where they intersect, and that becomes our instantaneous center. And then we can work from there to calculate the angular rotation of that link BD. This is another problem where we can do this. Again, here we have velocity at point C is going to look like that, and velocity at point B is going to look like that. And again, we can use those two velocities to actually find the instantaneous center, and then we can do more work to figure out the rotational rates of the different links in this whole linkage. That's another problem we're going to do. Okay. Then finally, the last thing that we're going to do, which is actually more related to the stuff that we did in the previous lecture, where we were talking about the relative motion analysis, but we were focusing on velocities. Now we're going to take a look at accelerations, and I might ask you to sort of remember that there was an expression we came up with for relative acceleration where we talked about the fact that when you have know the acceleration of one point and you want to find the acceleration of another point, and there's a rotation, you also end up with two terms that represent a tangential acceleration as well as a normal acceleration. And so here's a situation where we have a window. There's a lot going on with hinges and links here, and so AC is going to be rotating. The axis goes through point C. Point AB is going to go in a plane motion, and so as A goes in a curved path, it's going to have some acceleration. Notice here they have it labeled a normal component of acceleration and a tangential component of acceleration. And so those are some of the things that we're trying to figure out, again, using sort of relationships between two different points. So as a reminder, we had that for the velocity expression, the velocity of point B was equal to the velocity of point A plus the relative velocity of B relative to A. But when we take the time derivative of these expressions, we actually find that the last term talks about the acceleration of B with respect to A, and there will be, as I said previously, a tangential and a normal component. Think about when objects move in a circular path, there's the possibility that they're increasing their speed, which speaks to a tangential component of acceleration. They're also, as they're going in the circular path, are undergoing centripetal acceleration, and that's the normal component. And so here we're seeing that the acceleration of B can be found by knowing the acceleration of A, and then these two terms of the acceleration of B relative to A. And so in this picture, they're sort of showing this, how, what the terms are as A is going through these, AB is going through sort of a curve path. A and B can have their own accelerations, and we can sort of use the acceleration of A to figure out what the acceleration of B would be. The things that we'll need to know is how is that rod AB, what kind of angular velocity does it have, what kind of angular acceleration does it have. That will help us find these terms right here. And pretty soon, right down here, we see how we express them. And hopefully these look familiar because we did derive these in a previous lecture. The tangential acceleration is the angular acceleration crossed with the position vector of B relative to A. And the normal component of acceleration is minus omega squared R of B with respect to A. And that's just the centripetal acceleration. So here we have the terms all written out once again. how we find the acceleration of b given the acceleration of another point. And so this is basically, it's very similar to what we did in the previous lecture with relative velocities, but now we're just doing it with acceleration. And so, for instance, again, we can look at these linkages, and so we know information. So, for instance, we know that as AB is rotating, it obviously has an angular velocity of rotation, an angular rotation rate. It also can be accelerating. Its angular rotation rate can be changing, and so there's an alpha. This is going to make point B have both a tangential and a normal acceleration. And so we can find those values of, what's going on at point B, given our knowledge of what happens at point A. And then also we could use information about point B and then use it to infer some relationships to the motion of point C. So we can kind of move along. Some of the things here that become useful is, for instance, we might not know exactly what the rotational quantities are for link BC, but we can come up with expressions of the acceleration of C with respect to the information we have of the acceleration of of B. But one of the things that will help us narrow down quantities is that the acceleration of C is strictly horizontal, which means it only has an x component. And so if we have any expressions for the y component of that acceleration, we know that they have to go to 0. And that condition can help us find, for instance, maybe the angular acceleration for that link BC or its angular velocity as well. So basically the procedure that we go through is we sort of figure out what our coordinate system is. We figure out what's happening with the object. We want to indicate what are our points A and B, and what do we know about their angular velocity, their angular acceleration, and what is the position vector of point B relative to point A. And then we can use this equation to write out, given the information that we know, and then we basically make it into sort of algebraic expressions, because we probably will break it down into components. If we find that one of our answers is negative, it means that we sort of assumed a particular rotation, but it's in the opposite sense, and so that's not a big deal. And we just go through the process of solving the problem. Some other things that we're going to kind of come back to is that, things we've looked at before. We talked about gears. And remember, one of the things we found is that for the two gears to be working together properly, they would both have to have the same tangential acceleration at their outer edges, because those 2 points touch and they have to be moving together. That will end up telling us something about the relative rotational accelerations of each gear, also depending on their relative sizes. The one thing, though, that we can't say is the same about both the gears is that they won't necessarily have the same normal components of acceleration. Those don't have to be the same. And then also we can talk about rolling is another example where we can think about what would be the angular accelerations of different points on the wheel, especially when we're thinking about if it rolls without slipping. Point A has no velocity. That can be used as an instantaneous center of 0 velocity. And we can use information about velocity at different points, and then we can also use that to we can move on and then find some points about acceleration. For example, because the whole wheel is rotating with an angular velocity, it will absolutely have some sort of normal component of acceleration. It will also because it's going to be a different point as time goes on. It will have a tangential acceleration as well. And that's where we're going to stop with this. It's been great. We didn't want the semester to end the way it did, but we hung in there, and now we've done it.